The engineering landscape operates under an assumption. To build an advanced LLM application, you have to construct a massive, highly autonomous framework. Production-grade LLM design actually starts with a much stricter baseline rule. Developers must optimize for the absolute simplest solution possible. For many applications, a single LLM call enriched with retrieval and in-context examples is entirely sufficient. When teams start scaling their systems, they frequently turn to third-party drag-and-drop graphical interfaces or heavy agent software development kits to move faster. These abstraction layers automatically chain calls and parse tools, but they also obscure the underlying prompts and model responses. When an error occurs deep inside a chain, debugging these abstracted layers becomes exceedingly difficult. The most successful production implementations we see eschew heavy frameworks. They rely on building primitive, composable architectures directly from the core LLM APIs, keeping the system logic completely transparent. The industry frequently groups any multi-step LLM implementation under the broad label of agents. Architecturally, we draw a strict boundary between two distinct types of systems. Workflows are deterministic systems, where language models and tools are orchestrated entirely through predefined, hard-coded programmatic paths. Agents operate differently. The language model dynamically directs its own execution loop, altering its actions on the fly based on environmental feedback. Operating without predefined tracks gives agents the flexibility to handle open-ended problems, but that autonomy requires trading away the strict latency controls and cost predictability of a workflow. Developers should only cross the threshold from deterministic workflows to dynamic agents when the task complexity strictly requires model-driven decision-making to reach a resolution. To build these systems, we start with the atomic building block shown here, the augmented LLM. This is a central language model actively connected to distinct peripheral capabilities, specifically retrieval, tools, and memory. Current models actively leverage these enhancements. Using standardized client implementations like the Model Context Protocol, the LLM can pause its generation to fetch real-time data or execute an external task before returning its final response. By linking these augmented blocks together, we get the first architectural primitive, prompt chaining. This topology decomposes a complex task into a linear sequence of distinct steps, where the output payload of one model becomes the direct input for the next. Because the path is linear and deterministic, engineers can insert strict programmatic gates between nodes to verify intermediate outputs. A script can check if a generated outline meets specific criteria before allowing the final drafting node to execute. A common engineering use case is multi-stage content processing. One model generates an initial piece of marketing copy, passes it through a verification gate, and hands it to a second specialized model for translation. Breaking the process apart isolates the complexity of the task. Prompt chaining trades the higher latency of multiple calls for significantly higher accuracy. When an application handles a wide variety of inputs, we use a routing workflow. As shown in this diagram, a classifier node separates concerns by categorizing an incoming data stream and directing it into distinct specialized downstream branches. This prevents prompt dilution and optimizes resource allocation. Standard, highly repetitive API queries route to a fast, cost-efficient model, while complex edge cases automatically route to a heavier, highly capable model. Some processes require simultaneous handling rather than sequential steps, using a topology called parallelization. A single input triggers multiple language model tracks running concurrently, which then aggregate their results into a single final output. In the sectioning variant, a larger task is broken into independent subtasks. For instance, one model processes the core user query, while a second model simultaneously runs a strict guardrail check to screen for inappropriate content. In the voting variant, engineers run the exact same task multiple times across concurrent nodes with diverse prompts. This is heavily utilized in automated vulnerability scanning, where multiple models review the same code to increase the statistical confidence of the final assessment. Utilizing branching and concurrency structures ensures that a single model call is never overloaded with conflicting instructions or multiple distinct roles. When a task is too complex to predetermine the necessary subtasks, we use an orchestrator worker's workflow. Here, a large central orchestrator node analyzes the input, dynamically generates temporary worker nodes on the fly, distributes the data, and absorbs their results. The distinction between orchestration and parallelization is structural flexibility. In parallelization, the concurrent tracks are hard-coded by the developer. In orchestration, the number and nature of the subtasks are determined topographically by the orchestrator based strictly on the immediate input. If a coding product needs to implement a repository-wide feature, the orchestrator analyzes the codebase, determines exactly which files require modifications, and spins up a dedicated worker specifically for each of those files. To ensure quality control, engineers implement an evaluator optimizer workflow. This is a dedicated, continuous feedback loop where a generator node produces an output and sends it to an evaluator node, which fires back a critique and triggers a rewrite until the output passes. This loop requires two criteria to function. The evaluation metrics must be explicitly measurable, and the language model's output must demonstrably improve through iterative refinement. Dynamic orchestration provides the architecture needed to scale horizontally across unpredictable datasets, provided the feedback mechanisms are airtight enough to verify the temporary workers actually complete their delegated tasks accurately. We cross the threshold from deterministic workflows to fully autonomous agents when dealing with completely open-ended problems, where mapping out a fixed operational path in advance is impossible. In this execution loop, an agent receives a prompt, independently formulates a plan, and executes a tool command into a live environment. The return signal provides ground truth, execution data, or error codes, which triggers the agent to formulate a revised command based on reality. Autonomy carries the distinct risk of compounding errors. If an agent misinterprets an environment signal, it can loop indefinitely. Strict programmatic stopping conditions, like a hard cap on the maximum number of iterations, are mandatory. Customer support applications succeed with this model because they blend conversational dialogue with precise programmatic actions, like accessing an order history tool to execute an API-driven refund. Coding agents use this autonomy to resolve complex, verified GitHub issues. They iterate on codebase changes, run automated tests, and use the pass or fail results from the compiler as perfect, objective feedback. Scaling an autonomous loop safely relies entirely on a trusted environment. The developer must ensure the objective feedback returned from external tools acts as the absolute true north for the agent's decision-making process. Regardless of whether you build a simple linear chain or a fully autonomous loop, the entire system hinges on one mechanical dependency: the language model's ability to successfully invoke external tools. Just as human users require intuitive interfaces, language models require an agent-computer interface, or ACI. A poorly optimized, dense JSON tool schema is the programmatic equivalent of a cluttered, impossible-to-navigate dashboard. Complex tool requirements create formatting overhead. If a model has to meticulously calculate string escaping or count exact lines of code, it expends its available token bandwidth on structural formatting rather than the reasoning required for the task. Consider a tool requiring a code diff. Forcing the model to predict line counts in a header causes syntax errors. Mistake-proof the tool by altering its format. Replacing diff calculations with absolute file path rewrites ensures perfect execution. Effective ACI formats closely mimic the natural text structures the model encountered during its initial training data, ensuring it does not write itself into a formatting corner during execution. An agent possesses no inherent capabilities outside of its prompt. It is only as intelligent as the parameters and the clarity of the tools it is permitted to wield. Success in deploying large language models requires matching the absolute simplest architectural primitive to the specific problem, rather than rushing toward maximum complexity. Maintain strict simplicity and determinism in your system design for as long as your specific use case allows, optimizing single calls before adding chains or routing branches. When introducing autonomy, enforce structural transparency. Force the agent to output explicit, visible planning steps before it is allowed to execute any actions against an environment. To scale from a single API call to an autonomous codebase editor, engineers have to treat the agent-computer interface with the exact same rigor, testing, and optimization as the system architecture itself.